Hello all. In this lecture we're going to talk about memory in Java. Specifically what happens when you call a method, like this one here, using primitive variables, object type variables, and talk a little bit about static stuff too. So pause the video right now and see if you can figure out what this does. I'll wait. If you said 5, the best number, you are correct. Why does this make sense though? Here we're calling my method, sending it the variable a, which contains 5, and now we're calling it b here, which I guess sort of makes sense if you think about it as the method defining what it wants to call its own parameters. But then we assign 10 to b. What happens? Why doesn't that change a? The answer is we need to look at the call stack. A stack in computer science is basically a box. And on top of this box, another box, and another box, and another box. It works just like a stack in real life. Think about really heavy objects, for instance. If you had a stack of heavy, I don't know, stone blocks, the only one you could ever really access, move or remove, is the one on top. The same principle works here. When you actually make a method call, Java creates a virtual stack. We'll start with the main method. This is the first method call in the entire program. It's called by the system. So I'm going to place a stack entry down here and label it main. So what goes in here? Well, this is where all the local variables for a method end up. I'm going to divide it into 3 parts: type, name, and value. So let's take this variable here, int a equals 5. When this code is run, we have an int variable placed in the first entry. Its name is a, and its value is 5. Okay, easy enough. The next line of code, a method call to my method sending it a. When this runs, we place a new entry on the stack. And this new entry is eventually going to completely prevent all access to this bottom one. This entry is for my method. And just like before, we store the type, the name, and the value of the variables in this method. And what's the first one? Well, the parameters, right here. So, int b, well, what's its value? Well, the answer is Java is a pass-by-value language. There are other types that we're not going to talk about right now. But what happens is, when you call a method, the value of the variables that you send it, in this case 5 for a, are copied into the new method's call stack. So in this case, the value 5 is copied into this position here. This is a separate position in memory. It's completely disconnected from the main method. You can probably start to see why changing b has no effect down here on a. Okay, so once we have copied all the values from the sent parameters to the receiving one, we can start executing the code in my method. First line of code, b is equal to 10. Easy enough. Now we define a new variable. Why is it new? Because a, which is defined in this method, the main method, is completely inaccessible to the code at this point. It might as well not even exist. Everything underneath this stack could be thousands of entries long. Everyone could have an a in it. Doesn't matter. As far as it knows, a does not exist anywhere else. So we go ahead, int a, and we assign it to 20. All right, at this point we could do more complicated code. We can print these out. that sort of thing. But we don't. Instead, we just return. When this happens, we pop or remove the top entry off of the stack. And that way we can go back to the one underneath. It looks like this. You know, in a digital sense. Okay, so that entry in the stack is gone. We're back to the main method now, where we left off. System.out.println A. Here we have A, its value is 5. And that's why that outputted 5. Okay, let's take a more complicated example. Okay, new program here. Main method, all it does is call my method 2. Here's my method 2, and all it does is call my method 2. What happens? Well, we have to figure out what's the stack doing. So, we're in the main method, and we have no variables. It's a pretty simple stack. Now we call my method 2. Fair enough. Now we call my method 2. There's no reason why it couldn't call itself. As far as the system is concerned, it's just another method it could call. Okay, now we call my method 2, and my method 2, and my method 2, and so on and so forth. What eventually happens is the system runs out of memory. You might be thinking, well, that can't be because this is zero-sized. But in reality, there's one more thing in here that we have to keep track of, and that is our current position in our code. There's a hidden pointer here that says, I was here in the main method. I was here in my method 2. And each one of them has that. It takes a little while, but you can eventually make the computer run out of memory. If you try this, Java will quickly, hopefully, cause an exception that kills your program. Okay, let's look at something a little more complicated. Okay, let's look at the return system. Simple program, int a equals my method 3, and my method 3 simply returns 5. How does this look? Well, we're starting in main with an entry on our stack. First line of code, we define a variable which is of type int. Its name is a, and its value is assigned to the output of this method. Okay, so we can't actually put anything here yet. We have to add an entry onto the stack for my method 3. My method 3 has no parameters, so this is pretty easy. And all we do is simply return 5. This is how we actually get a value back out of a method to the one below it. And the way we do that is simply moving the number 5 into this position wherever the assignment is back in the calling method before we actually do the pop. This is done with a copy, and whatever was in A is just simply overwritten. Okay, a slight modification to that last program. We now are using a random object to return a random number rather than simply just 5. Small change, right? Well, this is going to cause us to look at a new area of memory, which I'm going to call the heap. The heap is where all the objects in Java are stored. We'll talk more in detail about this next. Let me just show you what happens when this program runs. First off, put our first entry on the stack. Again, int a is set to the output of my method 3. Okay. New entry on the stack from my method 3. All right, random rand equals new random. This has two parts to it. The first part we'll handle in the stack. We are simply creating a variable of type random called rand. The second part creates a random object. The objects don't go in the stack, not in Java. They go in the heap. The heap is another area of memory that is distinct from the stack. You can think of it as unorganized, and that's why I've tried to make it look like a cloud or so here. But this is where all the objects are allocated, where they live. And so we have a random object here. So what does this equal sign do? Well, we know that object variables store the location of the objects. We'll represent it with an arrow. Easy enough. Okay, next we return random.nextInt5. Let's say the random number that came up was 3. Simply copy this into here, and then we pop this entry off the stack. Notice that this object is still alive. Well, in a sense. This random object here, which was not in the stack, was not impacted by the stack pop. It still exists, but it is inaccessible. If you remember, this is what we call garbage. Eventually the garbage collector will come along sometime later and remove it from the heap. One more quick word about the heap. Let's say that I've defined a very simple class called myObject. And all that's in there are these two instance variables, A and B, both of type int. And now we have this code over here. We do have a stack entry somewhere. I haven't given you which method this is in. But somewhere, there's a stack entry for the variables. So let's figure out what happens. MyObject O. So we have type MyObject. Name is O. Create a new MyObject object, which we know goes into the heap. I'm going to draw it as a square. It is of type MyObject. And as we saw last time, we're simply going to make a point there. Okay. What is in this space here? Well, it's got its own table, just like each stack entry, containing all of its variables. So we have int A and int B, and right now they are both initialized to their default values of 0. Each instance of an object has its own table. That defines the state of this object. Okay, so let's run through this code really quick. O dot A is equal to 5. O dot B is equal to 10. Okay, now we have my object P equals 0. This is defining a new variable, but not a new object. We say my object P, and this is equal to O. Well, that copies the contents of the O variable into P. And what is in O? A reference to this particular object. That's simple. Now I have two variables pointing to the same object. P dot A equals 15. Well, go into P, go into this object, go into A, and set it to 15. Because these two references are pointing to the same object, they both see the variable A as being 15. you were to ask systemout.println O.A, you would get 15, or P for that matter. Okay, now we're going to create a new variable, my object Q, and set it equal to a new object of type myObject. And these are initialized to their defaults. And now we say, oh, one last thing. And now we say Q.A is equal to 20. So as you can see, within the heap, each object instance has its own copy of its instance variables. If there were methods in this class, and you called the method on this object, this is the only one that we modified. They're disconnected from each other. Okay, now for the real fun stuff. We're still going to use myObject. Here I have a main method that creates a myObject object and a variable A, and assigns some things in here, and then calls myMethod. My method takes in an int and a myObject, sets that int to 60, sets its object, or sets its myObject equal to a new myObject before setting its parameters. What is the value here of O.A and O.B? Can you figure it out? Pause the video real quick. I'll wait. Are you back? The answer is O.A is 20 and O.B is 40. Don't believe me? Let's look. So, start the main method. Create our entry on the stack. First thing, create a variable of myObject. Its name is O, and it is assigned to a new myObject instance. Okay, now we create an integer variable, and its value is 5. Set O.A equal to 20 and O.B equal to 40. Now we call myMethod. MyMethod takes in two parameters, an integer called B and a myObject called P. And remember, the value of these variables is copied into here. So, A, or at least the value of A, is copied into B. And O, the value of O, is copied into P. Okay, good so far. Now, the first thing that this method does is assign B 60. Fair enough. And now we assign P equal to a new myObject. And set P.A, sorry, should have done this, and set P.A equal to 70 and P.B equal to 80. Okay, at this point, the method returns, and we pop this off the top of the stack. So, what is the value of O here, .A and B? Well, O.A is still 20 and O.B is 40. But let's make one small modification. Okay, so we are right before our call to my method. I'm going to remove one line of code from my method. This one. We will not assign P to a new object. Let's look at what happens. Add our new entry on the stack, or my method. And it has an integer b, and a my object p. And these have their values copied from down here. First thing we do, set b to 60. And now we don't set p to a new my object. Instead, we set p.a equal to 70. p.a is equal to 70. And p.b is equal to 80. Now, we pop this top entry off the stack. And just by making that one change, now it's possible for a calling method to have the contents of its objects changed by a called method. Keep this in mind. One last thing I'd like to show you. So that's what happens with instance variables. But what about static variables? Here I've added a static variable int c to the myObject class. Remember, static variables, static methods belong to the class, not any particular object created from that. So let's see what this code over here would do. Let's just say we're in some method here. And we create a my object, O, equal to a new my object, int A0, int B0, that points up there. Okay, O dot A is equal to 20, and O dot B is equal to 30. Now we create another one, my object P, and I'll create another my object here. P.A is equal to 40, P.B is equal to 50. And then my object.c is equal to 60. Where's c? Neither of these objects have a c. And the answer is, again, it's in the class. And classes are stored in their own special area of memory. It used to be called the permanent generation. The idea was that the classes would be loaded into this one area of memory where they would be permanent. It's not really true anymore. The way it works is we designate off some portion of the heap, and we say all classes go here. So when the program is started, before any other code runs, all the classes are loaded into memory. And classes can have variables. They can have methods. So they get their own table. And inside this table, int c, which starts at a 0. The references in here are known as global. Any code, anywhere in your entire program, can access the static variables, the static methods, located inside the classes. If they couldn't, you'd have a problem, because you need these classes to create the objects from them. So, when we say myObject.c, we're referring to the class right here, this. The class myObject.c is equal to 60. Because this is located outside the stack, any changes you make in a method, who knows how deep in the stack, will show up to anything that uses this. That's why it's known as global. There is exactly one class in the system called myObject. Therefore, there is only one C. But you can create many instances of the objects myObject from the class blueprint. And each one will have their own instance variables, A and B. I hope that clears up a lot of this for you.